I'm Andrew Smith, and this is my video lab report for Lab 5, which dealt with the motion of falling objects. For the lab, I compared two objects that fall at different speeds due to differing drag forces. This was done by analyzing a video in Tracker and creating models in VPython. I first recorded my two videos and analyzed them in Tracker. I began looking at each before the objects were dropped. In the first frame of each video, I set the origin of my axes as close to the center of the object as I could, and then shifted the axes so that the ball would be traveling in the positive y direction. I then used a calibration stick to set the size of each object for the video clips. The tennis ball was found to be 0.065 meters, and the paper was 0.045 meters. The time between frames for each video was about 1/33 of a second. For the tennis ball, the mass was found to be 0.057 kilograms. The original position was found from the Tracker video. Since the video clip started with the object at rest, velocity starts at 0. The value for delta t comes from the time step in the Tracker video. For the paper, the mass was found to be 0.045 kilograms. The original position was found from the Tracker video. Again, the object starts at rest, so the initial velocity is 0. The value for delta t is based off of the time step from the Tracker video. There are two forces acting on the object while it falls, gravity and the drag force. Gravity is given by the formula F is equal to mg, where g is a constant equaling 9.81. The drag force for this lab, which is viscous drag, was given as opposite of the motion of the velocity and proportional to the magnitude of the velocity. This makes the equation for drag equal to negative b times velocity times the magnitude of velocity, where b is a constant determined from the experiment. To compare the various models, I graphed all three scenarios against each other. As can be seen, the graph for the gravity-only model has a much higher final position than the actual model. This makes sense as the force of drag works opposite to the force of gravity. The b value for drag was found to be 0.055, which is a fairly small value. Here I compared the various models using the paper instead of the tennis ball. The models worked out in a similar fashion, with the gravity-only model having a much higher final position than the actual data. Here the b value was found to be 8, a huge value, but one that makes sense given the fact that the paper both had a higher surface area and less weight than the tennis ball, which are both factors that affect the drag. The what-if question deals with throwing the object down instead of dropping it from rest. In both the gravity-only and gravity-drag models, the object would accelerate much more quickly. However, since drag is ignored in the gravity-only model, the object would accelerate indefinitely, whereas in the gravity-drag model, the object would stop accelerating once terminal velocity was reached. Looking at the slower falling objects' graphs, only the one that takes drag into account would reach terminal velocity. This is because terminal velocity is directly related to drag forces, as it is where F gravity and F drag are equal.